Okay, welcome back. What? Oh man, who turned that back on? There we go. It's too much. Okay, there we go. Start again. Okay, welcome back. What are we working on today? Anything cool or weird, interesting, broken? Broken's always good. You can always find something to fix. Loading up. I know it takes a few minutes to get connected to Wi-Fi. Check in, see what people are up to. Okay. What the average number should be. Okay, so there should be like a number in that year, 2017. Yeah. Yeah, what do you go up to now? So it's just one area where you go back in and get that table again. So it should be in the middle. Yeah. Maybe it was like revealed here, and then I found it. Very specifically weird, but standard process for getting a table into Canvas. So the main thing is like using CSV, and that
So I think we've done like some playing around with like data exploration and that kind of thing. So I wanted to show like with this transistor data set, because as I was walking around, it seemed like some people kind of playing around with it or looking at different steps there. So once, the nice part about like Pandas data frames is that you can grab different column, like you don't have to figure out like, all right, is this column 0, 1, 2? You can grab it by the label of that column. So if I want just the transistor count, I can start typing MOS and hit tab, and then it'll show me like, all right, do you want MOS process or MOS transistor? I want the transistor count. And then now I've got a data frame that is just that transistor count. And I could also like try plotting that transistor for date of introduction. And then let's put it as like circles. And if I just plot it, then it kind of looks like nothing was happening for the first 30 years of transistor work, because it's an exponential growth. It wasn't a linear thing. It's not like we added a little bit at a time. We're adding like every time. It was mostly like the area that we could use was getting bigger and bigger. So and transistors were getting smaller. So that's why ended up like doubling every 2 years, because it was, now you've got an extra X by X, not just like you're not stacking them up one after the other. So instead of looking at a plot, I want to look at a semi-log Y. And again, I'm just kind of like exploring data right now, just seeing like what things look like. Now I see something that looks a little more linear on a log scale. So every 10 years, we're going up by, let's see, 80 to 90, 10 to the 4, 10 to the 6. So like 2 orders of magnitude every decade, something like that. So it's a lot of transistors kind of coming into here. Another way that you could do that, you could take like log 10 of that. If you want, then you just have to keep track of like, this is now 10 to the 3, not 3. If you take a log, so you can manually kind of take a log of a variable. But semi-log Y works really well, so, and it does it for you, and it keeps the axes labeled nicely. But so there's a couple of parts to this question where it's asking like, just for like what happened in the year 2017, like just looking at what was the data there, and then the other part is, can you color them based on the designer, like just looking at one set, just looking at a couple of slices of that data. So let's look at this data set again. And we have like a few different designers. Some of the popular ones, at least that I know, are like Intel, Samsung, AMD. Apple has a few on the list, but Intel has like a lot. So one thing that I could do is just see what was Intel doing for the last 50 years. So let's try that. So I'll say transistors of transistors. And now I'm going to say designer. And set it equal to Intel. So I'm creating a Boolean operation, like when the designer is Intel, it's true, everything else is a false. So it's going to cut out everything except for Intel data. So all of the designer is Intel data. And now I've got 62. So there were 62 different processors from 1971 up through 2016. Cool. So I'll call this like Intel data, right? Intel is now going to be this data frame. And instead of looking at, actually, let's leave this. And then look at Intel. So if I look at like what was Intel doing over this time, it's like connecting all of those dots is one way. And the lines are not really super helpful because like this vertical line going in the same year is not really, it's not like it's saying that things changed in that 1 year. It's more, so it might make more sense to say like let's put those in squares. So now we can say like here's my Intel data and everybody else was doing something else. Well, like this is a great way of indexing. This Boolean indexing is super powerful for all sorts of stuff. So I could do the same thing for just the year 2017. And only get data from the year 2017. And now I can just look at transistor count or see like who, all the different designers, like who was producing something in the year 2017, but all sorts of like data exploration kind of stuff. But I thought that might be, at least based on what I saw so far, like where people are at, might be a nice way of looking at this.
Yeah, that'll work. Yeah, so now it's giving you your transistor mean and average date, which should be 27.
Hardest thing to measure. Let's just measure that.
So we were just playing around with like how do different functions work, and like I don't remember syntax for how something works or how to change what I want. But if I look at like length of transistors versus the length of transistors dot drop and drop NA. Oh yeah, I want to print both of them, right? If I just directly go in and drop all the NANs from that transistor data frame, then some of the NANs are actually coming from like different rows. let's see if there's any. Oh yeah, like over here in this bottom right corner. I don't really care if I don't know the area because I'm not using the area to calculate anything. But I do, so I would still want to keep this row, even though there is an NaN in that row. So one way is like subset, like just only give me the data that I care about. But we were trying to figure out, shouldn't that like drop NA have more options to it? So here's our drop, if I could spell, drop NA. If I don't know how to use it, I can always add a question mark and figure out how it's supposed to be used. So it prints out, remember we talked about like doc strings? Every like built-in function is gonna have like a nicely documented doc string. And in this case, it's showing me like, all right, there's drop NA. I could change the axis, like maybe I want to drop columns instead of rows, but that's not what I want to do because I don't want to drop the entire MOS transistor count column. So I want to keep that. So that's not what I want. I could say like how I want to do it, like if it's present, drop that row or column, or if all the values are NA, then drop it. So only look at ones where the whole row is NA. But even still, that's not what I want. Really what I want is down here in this thing that says subset. So I can create like so if I can figure out how to use that option of subset, then I can just tell it, look at one column, and if there's an NA, drop that row. So coming down, keep coming, so it's showing me how and all and threshold, but then down here, there's this question of subset equals name comma toy. So if I give it a list of column names, it's gonna check those columns, and that's what I want. So now I could say drop NA of subset equals MO, yeah, it doesn't let me autocomplete. And now that last row that I was seeing before, like it would have been dropped, but now it's not dropped. Scroll up a little bit, see it, but row 185 is still there, even though it has that NaN because I created that subset. But mostly that was just, I just wanted to show the power of those doc strings, of those documentations. So now if I look at that, and all that is because I was able to look at how to use this function. Yeah, just the weekly reminder that question mark gives you a lot of information about how to use all these tools. Yeah.
Can you explain, like, for instance, where you're doing your Intel, you're trying to pull just the Intel data, while you're doing trans, and then in brackets again, trans designer.
Oh, in that one?
Syntax of that?
Yeah.
Because I would have just thought you do trans bracket designer, and that would pull it. Why do you put that first one in front of it?
So kind of breaking it apart into steps. First step is if I look at designers, then it gives me this, it's a data frame, but like a whole bunch of designers. So every row has a designer. So now if I say, all right, are any of those equal to the word Intel? Then I have a list or a whole data frame of true and false statements. But what I really want is I want to say if if it's false, don't show it to me, and when it's true, show it to me. So now I can say, use that Boolean operation of saying, plug all those true false statements into my array, into my data frame, and now everything that was false does not get shown. All the true statements do get shown. You know, but that's why you end up with like kind of a weird syntax of like trans of trans equals something. Yeah, cool. Yeah.
Okay, for that question B in number 2, it says creates log y-axis scatter plot. All are the data according to the designer. Is that asking us to all are the data according to every individual designer, or just for one designer?
Each individual design. So every designer has a different color, and that part is yeah. It's okay if you cycle through the same colors, as long as it's not like red, blue, red, blue, red, blue, or something. But as long as you have a few different colors, like, so you can start to tell the difference of what's going on. Some people get really into it. They like create like a color map and like go through the entire rainbow of colors, so that every designer has a different RGB value than every other designer. Or you can change like the color and the shape of the symbol if you really want to tell the difference. But as a starting point, just different colors, different designers. What was I gonna say? Oh, I got rid of that Intel one. But here, what I wanted to show, again, kind of a reminder, like if you can do it once with the script, you can do it as many times as you want. So we can cycle through, and Python's pretty like its for loops are pretty powerful. We can go through any list-like structure. It doesn't have to be like an index from 0 to something. So if I can say, oh, not that. If I can say designer data is something, and then plot that designer data, I can cycle through anything that this doesn't have to say Intel. This could say like designer, like the label, and put this whole thing in a loop. Or designer in transistor trans of designer. So I could take every name and loop through every name, right? Would that work? Any reservations on this? Yeah.
Because it's just like every time there's a new thing in design, or every time there's something in designer, it's going to be a new color.
Yes, yeah, it's going to give me a new color every time. It'll cycle through I think there's like 8 or 9 colors that it's going to cycle through. You know, because by default, as you keep adding more lines or data to every time you run plot, it tries to give you like a new color. It goes through a cycle. Anything else? Let's try it, see what happens. Oh, and let's give it a label, right? That would help. I know there's a lot of names on here, but does anyone notice something a little weird to start? It's weird. It's in a weird location, but
Duplicating names.
Duplicating. I think it's bbox 2. I've looked this up. If we want to get it out of the way. There we go. Why is it duplicating the names? Why does Intel keep showing up? Like here, there's like 4 Intels in a row. Yeah.
Isn't it like it reads the designer and every single time there is anything, it gives a new color?
Yeah. Yep. So right now, the thing that I'm looping through is every name. So Intel comes up, we already figured out, it comes up like 60 times. So it's going to plot the Intel data 60 times. Like it's going to create a subset of Intel 60 different times. So what I really want is just the one, I want Intel, but I just want it to show up one time. So there's a fancy function for that called unique. So I can create a unique list of stuff. Dot unique, let's see, autocomplete, no, not today. Oh, there it goes. Oh, and it does one, open close. So when I just look at the unique stuff, it gives me an array full of just the unique name. So Intel shows up once, Bell Labs just one time. I'm not getting repeats. I'm not getting 186 names that I'm trying to cycle through. So dot unique. And now we're starting to make some progress, right? Again, I think there's only like 9 colors that it cycles through, so there's other way, like if you want to keep giving it different colors, you can create a color map or all sorts of different stuff. Oh, but at the time. That's where we ended up today.